Now that we've decided about concavity, let us define what an inflection point is. Inflection point is a point that is continuous for f. So it's a point where the function is continuous and the concavity of the function changes there. Now it doesn't specify whether it changes from concave up to concave down or concave down to concave up. In my previous example, it changes from concave down to concave up at A. So A there was an inflection point. Right? So let's go ahead and see if we can find these using a particular method called the concavity inflection point test. It is very similar. As a matter of fact, it's totally analogous to the first derivative test for relative extrema. I'll try to point that out as I go. So let's just take an example here. We'll take f of x equals 2x cubed minus 9x squared plus 12x minus 3. All right. If this function here was what I was looking at, and I wanted to find the relative extrema, first thing I would do is take the first derivative and I would set it equal to 0. Why would I do that? I would do that, as we saw before, so I could find where the first derivative was positive or negative. And that tells me the function is increasing or decreasing. Okay? I'm going to do the exact same thing now with the second derivative instead, and that will tell me where the function is concave up or concave down. So it's the exact same process I'm going to go through. I'm going to make a sign chart and everything. The exact same process, but I'm applying this process to the second derivative to get information about concavity instead of information about increasing, decreasing. So we'll have 12x minus 18, and I would like to know where this is less than 0 or greater than 0, but to find that out, I will set it equal to 0 and make my sign chart. So in this case, if I just factor a little bit, I guess I can take out a 6 maybe. So we'll have 2x minus 3, I guess. And then that implies that x equals 3/2. All right, this is not a critical point. The reason it's not a critical point is because it did not come from the first derivative, it came from the second derivative. So what I'm going to call this now is just a description. It doesn't have any special name per se. I'm going to call it a possible inflection point. Analogously, in the first derivative test for relative extrema, this would be a possible relative extreme location. Now we just have a special name called critical value for it, but that's the role it's playing over there when you do the first derivative test. Is the possible relative extrema. So therefore, in this test we're doing right now, concavity plays the role of increasing, decreasing for the function, and inflection point plays the role of relative extrema for the function. Right? So it's just new information gleaned in the same way, but since I'm working with the second derivative, the information is different than when it's the first derivative. Right? It's about the curvature of the function and where it changes its curvature. Right? As opposed to the first derivative tells us where it's going up and down, and the relative extreme location is where it changes from going up to down or down to up. Right? So now I'm going to make a sign chart just like for a first derivative test, but it's not a first derivative test, it's a test for concavity. So something like this. Only have one number to put on here, 3/2. Again, this is basically the x-axis for the function, right? Just a modified version. And I want to know only about the second derivative in this case. So second derivative, I'm going to do the same thing. I'm going to make a test case. I'll test a number which is less than 3/2. 0 is a good candidate. And I plug it into the second derivative. And again, I use the factored formula to just make it easier to see what's going on. So I plug in 0, I get a negative for this factor. So negative times a positive is negative. Therefore, the second derivative is negative on the first interval. And again, I can play the idea that the multiplicity of this root, of all the roots, which only this one, is 1. So therefore, it has to change sign without taking a new test case and doing any computations. I know it has to be an alternating sign chart from what I said earlier, and so therefore, I can just put a plus there with confidence. All right, so what does that mean? Well, if f double prime is negative here, and f double prime is positive here, that means the original function f is concave down on this part of its domain, and it's concave up on this part of its domain. And because the concavity changes, it doesn't matter if it's negative, positive, negative, concave down, concave up, concave up, concave down. It doesn't matter, as long as there's a change at all. I'm going to call 3/2 no longer a possible inflection point. It is an inflection point now. Okay, so let's write out what we have. We now know that this function is concave down on the interval negative infinity to 3/2. It's concave up on the rest of its domain, barring the 3/2 value itself. 3/2 to infinity. And we have an inflection point at 3/2, comma I don't know yet. We have to plug it back in and find out. Okay, so we need to find f of 3/2. F of 3/2 should be 2 3/2 quantity cubed minus 9 3/2 squared plus 12 times 3/2 minus 3. Okay, trying to hurry through this. This 2 will cancel one of these 2's, so we'll get 27 on 4. Seems reasonable. Minus, this would be a 9, 81, minus 81 on 4. I'm going to write everything in terms of fourths now, just to make it easier for me. So I'll have a 36 on 2, which will be the same as 72 on 4, and minus 3 will be the same as minus 12 on 4. So let's see what we have. Negative 81 and a positive 72 is going to be what? A negative 9. Negative 12 is a negative 21. From the 27 will be a 6 on 4, if I'm not mistaken. I'm down to 3/2. So it ends up being 3/2. And we have our inflection point.